So last time we talked about how we can evaluate formulas by playing a game. But in general, computational view, that is when you're thinking about the formula as a problem as a computer scientist, is very, very useful. And there are lots of very much computer science concepts that come in both building the formulas and evaluating them. So whenever you're building a formula, whenever you're evaluating the formula, trying to read one, imagine that you need to write a machine that will respectively evaluate the formula or construct a formula out of the pieces. And one of the very important notions here that you probably have encountered if you've done any kind of computer science class is a type checking. So what's type checking? When you were a child, you might have had that game when you had different holes of different shapes and pieces of different shapes, and you were supposed to put a round piece into a round hole and a square piece into a square hole. So this is what type checking kind of is. You have pieces of different types, round, square, triangle, and you put them into different holes, different places in your formula. And you don't want to put a round piece into a square hole and vice versa. So here are the types that you will see in predicate logic formulas. The three main ones are the Boolean type. This is what you're familiar with. This is things that take value true or false. So predicates are Boolean, formulas are Boolean, and whenever you have two things that are Boolean, you can combine them using and, or, and not, and implication in order to get another thing which will also be of type Boolean. A completely different thing is elements from the domain. So if Booleans are things that are true, false, elements from the domain are, well, depending on the domain, it can be numbers, it can be people, it can be all sorts of things. And where you will see things that are of type elements is in predicate logic as input to predicates and inside of the quantifier construction. So what can you do with those element type things? Well, the main thing that you would do with them is, again, give them as input to predicates, making sure that you give the correct type of an element corresponding to the domain of a predicate. And also sometimes when they come from some common domain like numbers, you could use as operators functions that will take something from that domain and return something from generally the same domain. So for example, if you have two numbers, then their sum or product is also a number. And so you could, if you have a predicate that takes as an input a number, you could give it a sum of two numbers and you would still have the right type. Finally, there is one more type which is least prominent in predicate logic formulas. It occurs only in one place, in quantifiers. And this is a type of set or domain. So you only see it in the construction exist element in a set or for all elements in a set. And sometimes when people write a formula, when it's pretty clear what the domain is, they will even omit the in S part of the quantifier construction. But just for simplicity right now, let's not take the shortcut and talk about the quantifier as there exists X in S, which is where you will see something that's a set. So let me show you on an example. So suppose you have a formula for all X in Z, even X or odd X. So what are the types of different objects here? So we got two predicates that are connected by an OR. We got one variable X, which is an element, and it's a member of a set integers. Z stands for integers. So let's color it. So even and odd are predicates they take as input something of type element and return something of type Boolean, that is, return something that's either true or false depending on the value of that x. The OR operation takes two Booleans and returns a Boolean, so the whole thing after the comma is Boolean. By the way, comma here is just for readability. Sometimes people put comma under the last quantifier, sometimes they don't. It's up to you. And finally, we have the quantifier construct, which consists of quantifier, then x, which is an element, then in operation, which is actually a Boolean, and then the name of a set, z. And this whole quantifier construct returns a Boolean. So let's now think about it even more computationally. Let's think about machines for evaluating formulas like that. But let us start with simpler formulas, the propositional formulas that we studied at the beginning of this course. So in the world of propositional, everything is Boolean. Everything takes value true, false. There are no numbers, there are no sets, everything is just Boolean. And how do those Boolean machines operate? Well, for example, suppose you want to evaluate a propositional formula. You all know how to do it. You draw the syntax tree, then you start with the inputs and you go up the tree until you reach the top, and then you know the value of the formula. And you could think of every node in a tree as a machine that takes the values of two things underneath it, which are two Boolean values, and outputs another Boolean value. And if you're reading it as a formula, or even if you're looking at a tree, it kind of wants to see something of the form, something Boolean, then an OR, then another Boolean thing. So for example, it can be that the two things underneath it, the first one was true and the second one was false. You feed it to your OR machine, and it outputs something that's true. So it read the formula of the form something or something, and by that point, the first something was already evaluated to true, and the second something was already evaluated to false. So here is an evaluator machine. We could kind of switch it around and think about a builder machine, a construction machine. That's the machine that doesn't really evaluate things, but it constructs formula. So if you have a syntax tree and now you want to convert it back to a formula, when you want to write it down, you would use this construction machine. And here's how it works. It again takes two things of type Boolean, but now rather than thinking about them as specific values, truth and false, you just think about them as formulas. Formulas are of type Boolean. And when it gets two formulas of Boolean type, it produces another formula. It also will be formula, so it has Boolean type, which consists of the first thing followed by, in this case, an OR, and followed by the second thing. So hopefully this kind of shows how you could think computationally about constructing formulas and evaluating formulas. Later on in this course, and especially in your algorithm and data structures course, you will talk at length about how you could evaluate formulas like that, how you could check that the formula is written correctly, so all the things are of the right types and in right places, and how to do it efficiently. But that will be in your 2002. So let's now look at predicate logic formulas, where now we really do have a problem with all sorts of different types. Again, we got Booleans, which is our main thing. The final formula that we construct has to be Boolean, but we also got elements and sets of elements. And again, when we are doing the construction part, then we use and, or, not, and so on for Booleans, just like we did in propositional logic. But we need somewhat different machines to both construct and evaluate predicates and quantifiers. So what is a predicate? We talked about it a lot, but let's look at it again computationally. And here it might be useful to think about a predicate as a database query, because query is kind of like you give some inputs to, well, a machine, a query, and it gives you an answer. And it makes perfect sense to talk about what inputs you give it and what answer it gives. So a predicate takes several elements. They can come from different sets, but all of them elements, so variables for those elements, and it produces a Boolean. So your predicate always outputs a Boolean. And it may have one input, two inputs, three inputs, or sometimes in databases it can have 5, 6, 7 inputs. But in any case, it takes in a bunch of elements and it produces a Boolean. For example, an evaluation machine for a predicate less than or equal can take a number 4 and a number 2 and say, no, it's false. And what it produces as a Boolean is something that's either true or false, in this case, a false. So now we could use the same idea, turn around, in order to construct formulas. So how do we construct the simplest possible formula? If we have a predicate, we feed that predicate elements, and the output of the predicate is Boolean, so our machine will take elements, and maybe it will take the name of the predicate, or maybe it already knows the name of the predicate, and it will write it as name of the predicate, and then in parentheses, comma-separated list of the elements it got. So for example, it can be predicate P, you have element 1, element 2, and you output P of, in parentheses, element 1, comma, element 2. Sometimes when predicates are binary, such as less than, it outputs something in a slightly different format. For example, it gets x and y and outputs x less than or equal to y. But in any case, it still outputs something of type Boolean. Okay, so hopefully this kind of explained how you build predicates and how you evaluate predicates. One remaining thing in predicate logic that we didn't deal with yet is a quantifier. So how do you evaluate a quantifier? What do you need for that? Well, you need to know the formula, and you have to have a set and a name of an element from a set, like x or something. And this name has to be free in the formula. If that x is not in the formula, then why would you even bother to put a quantifier on it? So for example, you may have a formula for all x in integers, even x or odd x. And then what your evaluation machine will do, it will somehow figure out whether it's indeed true that for every element of that set, that formula is true for that element. And if so, it will say true. So the quantifier machine takes a name of a variable of type element, a name of a set of type set, and something that's a formula with a free variable the same as that name that you are given. And it will output a Boolean value. It will output true or false. So again, turning it around, how can we use that idea of evaluation to construct formulas? Again, if you get an element name, a set, and a formula with that element name occurring as a free variable, you could write them down as for every name in set, formula, parentheses of that name is true. Or actually, here I said formula in parentheses, but in general, if your variable occurs somewhere in this formula, you just write down that formula. So for example, if your element is called x, and you have universal quantifier, and your set is integers, and your formula is even x or odd x, then Your machine that constructs formulas will take that information and produce for all x in z, and then in parentheses, even x or odd x. So again, think about them as machines. They get an input of some types, and they produce an output of some type. And if they get the wrong input, well, they will give you an error. So somehow negation is the one which causes most trouble to people, unless they think as computer scientists, unless they think computation. For example, you cannot give not followed by a number or an element to an evaluation machine. It will say, oh, error, I don't know how to negate a number. I don't know how to negate a person. I only know how to negate Boolean error. Instead, what do you want to give to the machine is a not of some Boolean value. Then the machine can work, and it will give you a Boolean value, which is the opposite from that thing under the not operator. Similarly, when you are constructing formulas, and again that applies to predicate logic formulas mostly, if you give something of type element to a negation machine, it will say, error, I cannot negate something that's not Boolean. All I can negate is formulas. I cannot negate a person. I cannot negate things that are not true or falses. But if you give it a formula, it will output what you expect it to output, not followed by the formula. So again, when you're writing the formula, when you're combining things together, every time you put things together, think, would evaluation machine give an error? Would your construction machine give error on your second step if you give it that piece? If you're trying to do to and Susan, that's not going to work. But if you're trying to do even of two and feminist of Susan, that's totally fine. That's a Boolean.